Route-based taxonomy deep dive. Please consider subscribing to the channel. I produce videos daily covering AWS, Azure and GCP. Hit the bell icon to get notified of new videos. I appreciate in advance your subscription. Today we're exploring one of GCP's most sophisticated networking features, route-based taxonomy. This isn't just about organizing routes. It's about creating intelligent, hierarchical systems that can make autonomous routing decisions. Think of traditional routing as a flat directory where you manually manage every single route. Route-based taxonomy is like creating a smart organizational system where routes inherit properties, policies cascade automatically, and the network becomes self-managing. We'll also dive deep into next hop health tracking, GCP's ability to automatically detect when routing targets become unavailable and adapt routing decisions in real time. This is critical for building resilient, self-healing network architectures. By the end, you'll understand how to build routing systems that scale elegantly and maintain high availability through intelligent automation. Understanding route taxonomy structure. Route taxonomy in GCP follows a hierarchical model similar to organizational charts or file systems. At the top level, you have broad categories like production or development. Each level below gets more specific. The power comes from inheritance. When you define a policy at the production level, it automatically applies to all child categories, like production, web, and production, database, unless specifically overridden. This diagram shows a typical enterprise taxonomy structure. Notice how policies flow down the hierarchy, but lower levels can override inherited policies when needed. This gives you both consistency and flexibility. The key insight is that you're not just organizing routes, you're creating a governance framework that can automatically apply business rules to network behavior as your infrastructure evolves. Creating your first taxonomy, line by line. Let's break down every single line of the taxonomy creation command. The first line starts with G-Cloud Data Catalog Taxonomies Create. This tells GCP we want to create a new taxonomy container in the data catalog service. The taxonomy name Route Policies follows immediately. This becomes the unique identifier for your taxonomy within the project. Choose this name carefully as it will be referenced in all subsequent policy commands. The location global parameter is absolutely critical. It makes this taxonomy available across all regions and zones in your project. Without this, you'd need separate taxonomies for each region. The display name provides a human-readable name that appears in the console and documentation. The description is essential for team collaboration and governance documentation. The verification command shows you how to list all taxonomies and confirm your creation was successful. This is crucial in automated scripts to verify each step. Building hierarchical policies, every parameter. Now we're creating the actual policy hierarchy, and every line matters. The first command creates our top-level production policy. The command starts with G-Cloud Data Catalog Policy ID tags create followed by the policy name production. The taxonomy equals route policies parameter links this policy to our taxonomy container. This establishes the ownership and scoping relationship. The location equals global must match the taxonomy location exactly. The display name and description provide human-readable information that's crucial for team understanding and compliance documentation. These aren't optional in enterprise environments. The second command creates the web tier policy as a child. Notice the parent policy ID tag equals production parameter. This creates the inheritance relationship. The child policy will automatically inherit all parent policies unless explicitly overridden. Each subsequent policy creation follows the same pattern, but builds the hierarchy by referencing the appropriate parent. This creates a cascading policy structure that mirrors your organizational needs. Policy inheritance in action. This diagram illustrates exactly how policy inheritance works in practice. When you apply a policy tag to a route, that route doesn't just get the specific policy, it gets the entire inheritance chain. Look at the production.web.frontend policy. A route with this tag automatically inherits policies from production level, web level, and front-end level. This creates layered governance where broad organizational policies combine with specific technical requirements. The beauty is in conflict resolution. If the production policy says use premium network tier but the front-end policy says use standard tier for cost savings, the more specific policy wins. This gives you both consistency and flexibility. Notice how one route can effectively have multiple policies applied, but through inheritance rather than manual configuration. This dramatically reduces management overhead while ensuring consistent policy application. Applying taxonomy to routes, complete breakdown. Now let's dissect every line of the route creation with taxonomy. The command starts with G-Cloud Compute Routes Create followed by the route name Web Frontend Route. This name must be unique within the VPC. The network parameter enterprise VPC specifies which VPC this route belongs to. The destination range parameter 10.100.0.0/16 defines what traffic this route will match. That is all packets destined for that subnet range. The next hop instance parameter frontend LB tells GCP to forward matching packets to this specific instance. The next hop instance zone parameter US Central 1A is required because GCP needs to know exactly where that instance is located. The priority parameter 100 sets this route's priority in the routing table. Lower numbers mean higher priority. The policy tags parameter is where the magic happens. It applies the full taxonomy hierarchy to this route. The policy tags value is a full path that includes project, location, taxonomy ID, and the policy path. This complex string tells GCP exactly which policies to apply and where to find them in the hierarchy. The description parameter provides documentation that's essential for troubleshooting and team understanding. Never skip this in production environments. Next, hop health tracking overview. Now let's dive into one of GCP's most sophisticated features, automatic next hop health tracking. This is how GCP ensures that routes only direct traffic to healthy destinations. Traditional routing assumes that if a route exists, the next hop is reachable. But in cloud environments, instances can fail, networks can become partitioned, and services can become unresponsive. Health tracking solves this by continuously monitoring next hop availability. The diagram shows the health checking process. GCP automatically sends health probes to next hop destinations and tracks their responses. If a next hop becomes unhealthy, GCP can automatically fail over to backup routes or remove the unhealthy route from consideration. This isn't just monitoring, it's active route management that maintains network reliability without human intervention. Health check configuration, parameter by parameter. Let's break down every parameter in the health check commands. The first command starts with G-Cloud Compute Health Checks Create HTTP, telling GCP to create an HTTP-based health check called Web Service Health. The port 80 parameter specifies which port to probe. This must match the port your application is listening on. The request path/health tells GCP what URL path to request. Your application needs to respond on this endpoint. The check interval 10 seconds determines how often probes are sent. Shorter intervals detect failures faster but create more network overhead. The timeout 5 seconds sets the maximum wait time for each probe response. The healthy threshold 2 means 2 consecutive successful probes are needed to mark a target as healthy. The unhealthy threshold 3 means 3 consecutive failures mark it as unhealthy. These thresholds prevent flapping during temporary network issues. The TCP health check example shows a different probe type for database services. Notice how port 5432 targets PostgreSQL specifically. The intervals are longer because database health changes less frequently than web services. The HTTPS health check combines secure connectivity with application-level health checking. The shorter intervals reflect the need for faster detection on user-facing services. Root health check integration. This diagram shows how health checks integrate with routing decisions. When GCP performs route lookup for a packet, it doesn't just check route priority and destination matching, it also verifies next hop health. If the primary next hop is healthy, traffic flows normally. But if health checks detect a failure, GCP automatically fails over to the next available route. This happens transparently. Applications don't see connection failures or timeouts. The health checking system maintains state for each next hop, tracking not just current health but also health trends. This allows for sophisticated failover logic that can predict and prevent issues before they impact traffic. Notice how multiple routes can target the same destination with different priorities. Health checking ensures that traffic always flows through the best available path, automatically adapting to changing network conditions. Health-aware routes. Complete command analysis. Let's analyze every line of the health-aware route creation. The primary route command starts with G-Cloud Compute Routes create web primary route, establishing this as the main traffic path. The network, destination range, next hop instance, and next hop instance zone parameters work exactly like normal routes. The priority parameter makes this the preferred route when healthy. The crucial addition is the health check parameter, which links this route to our previously created health check. This enables GCP to automatically monitor the next hop instance and make routing decisions based on health status. The policy tags parameter applies our production web primary taxonomy, giving this route all inherited policies. The backup route follows the same pattern but with priority 200 and a different policy path. The monitoring command at the end shows how to verify your health-aware routes are working. The filter parameter specifically shows only routes with health checks enabled, making it easy to audit your health-aware infrastructure. Notice how both routes target the same destination range but different instances. When the primary instance is healthy, all traffic uses the priority 100 route. If it fails health checks, traffic automatically switches to the priority 200 backup route. Advanced health check strategies. Let's dive deeper into sophisticated health checking patterns. Basic HTTP and TCP checks are just the beginning. Enterprise environments need multi-layered health validation that can detect subtle service degradation before it impacts users. The custom health check command shown creates application-specific health validation. The request path /API/v1/health/detailed hits a comprehensive health endpoint that checks database connectivity, cache systems, and external dependencies. Notice the proxy header parameter. This is crucial for load-balanced environments where the health check needs to include proxy information. The host header ensures the application sees the correct host name, which matters for virtual hosting scenarios. The unhealthy threshold of 5 is higher than basic checks because detailed health checks might occasionally time out due to complex validation logic. You want to avoid false positives that could cause unnecessary failovers. Multi-region health monitoring. When your infrastructure spans multiple regions, health checking becomes more complex. You need to understand how GCP handles health checks across regional boundaries and what that means for failover timing. The diagram shows how health checks from different regions can have different latency characteristics. A health check from US Central 1 to a US East 1 instance will have higher latency than a local check, which affects timeout settings. The key insight is that health check results are region-specific but routing decisions are global. An instance might be marked unhealthy from one region's perspective but healthy from another's. GCP makes intelligent decisions based on the aggregate health data. This is why the region's parameter in health check configuration matters. You can specify which regions should perform health checks, optimizing for both accuracy and network efficiency. Monitoring is where health checks prove their value. Let's break down every parameter in the monitoring commands to understand exactly what information you're getting. The first command uses G-Cloud Compute Health Checks list with a custom format. The format parameter specifies exactly which fields to display: name, self-link, the full resource URL, and the check intervals that determine monitoring frequency. The second command dives deeper into instance-specific health status. The filter parameter uses GCP's filtering syntax to show only instances that have health checks associated. The format shows not just current status but also the timestamp of the last check. The logging query command is particularly powerful. It searches cloud logging for health check events, showing you the detailed history of health state changes. The limit parameter controls how many log entries to retrieve, and the format structures the output for easy analysis. This monitoring data is essential for understanding health check effectiveness and tuning your thresholds for optimal failure detection without false positives. Policy conflict resolution. In complex taxonomy hierarchies, policy conflicts are inevitable. Understanding how GCP resolves these conflicts is crucial for predictable routing behavior. The diagram shows a classic conflict scenario. The production parent policy mandates premium network tier for performance, but the cost optimization child policy specifies standard tier for budget reasons. Which policy wins? GCP uses a most specific wins approach. Child policies always override parent policies when there's a direct conflict. But here's the sophisticated part. Policies can also be marked as mandatory at creation time, which changes the inheritance behavior. The resolution shows how GCP handles this. The specific child policy takes precedence, but the system logs a policy conflict warning. This gives you visibility into when your governance rules are being overridden by specific requirements. Understanding this hierarchy is essential for designing taxonomy structures that provide both governance and flexibility. Advanced Policy Tag Configuration. Let's examine advanced policy tag features that go beyond basic hierarchy. The command shown creates sophisticated policy structures that can handle complex enterprise requirements. The first command creates a policy tag with restricted access. This means that only specific IAM principals can apply this policy to routes. It's perfect for security-sensitive routing policies that should only be used by authorized teams. The enforcement level parameter is crucial. Mandatory means this policy cannot be overridden by child policies, while advisory allows overrides but logs warnings. This gives you control over which policies are governance requirements versus guidelines. The data classification parameter adds another layer of governance. Routes tagged with this policy automatically inherit data handling requirements, which can trigger automatic encryption, logging, or compliance monitoring. The parent policy reference shows how to build complex hierarchies where some policies enforce mandatory requirements while others provide flexible guidelines. Route Health Status Dashboard. Understanding the current health status of your routes is critical for operations. The dashboard view shows 4 key health states that routes and their next hops can be in. Healthy routes are actively passing traffic and have recent successful health check results. The 47 healthy routes shown represent the majority of your infrastructure operating normally. Unhealthy routes have failed health checks and are not receiving traffic. The 3 unhealthy routes need immediate attention. GCP automatically routes around them, but you should investigate and remediate the underlying issues. Degraded routes are passing health checks but showing performance issues like increased latency or partial failures. The 8 degraded routes are still functional but warrant monitoring. Unknown status typically means health checks haven't run recently or are in transition. The 2 unknown routes might be newly created or experiencing health check connectivity issues. This real-time visibility into route health enables proactive operations and quick problem resolution. Let's walk through health check troubleshooting, step by step. When health checks aren't working as expected, you need a systematic troubleshooting approach. Let's break down the diagnostic commands, line by line. The first command checks if the health check configuration exists and is properly formatted. The format parameter shows the key configuration details, including ports, paths, and thresholds. The second command verifies that routes are actually using the health check. The filter parameter specifically looks for routes with health check references, showing which routes should be health aware. The instance connectivity test is crucial. Health checks must be able to reach the target instances on the specified ports. The SSH command tests this connectivity from GCP's perspective. The firewall rules check is often where problems hide. Health check traffic comes from specific GCP IP ranges, and your firewall rules must allow this traffic. The logging query at the end shows health check execution details, including any error messages that explain why checks are failing. This is usually where you'll find the root cause of health check issues. Automated route failover. Understanding GCP's automated failover behavior is essential for designing resilient architectures. The timeline shows exactly what happens when a primary route's next hop fails. At t=0, the primary instance begins experiencing issues but hasn't failed health checks yet. Traffic continues normally because health checks are still passing. At t=30 seconds, the first health check failure occurs. GCP doesn't immediately fail over because the unhealthy threshold hasn't been reached yet. This prevents flapping due to temporary network issues. At t=90 seconds, after 3 consecutive failures, based on our 30-second check interval and unhealthy threshold of 3, GCP marks the route as unhealthy and begins routing traffic to the backup route. At t=120 seconds, all new connections are using the backup route. Existing connections may continue briefly before being migrated or timing out naturally. This automated process typically completes in 2 to 3 minutes, which is significantly faster than manual intervention but slow enough to avoid false positives from temporary issues. Performance optimization strategies. Optimizing route taxonomy and health check performance requires understanding the trade-offs between detection speed, resource overhead, and false positive rates. The optimization strategies shown balance these competing requirements. Shorter health check intervals provide faster failure detection but increase monitoring overhead and can overwhelm struggling instances. Regional health check distribution is crucial for global applications. Health checks should originate from multiple regions to provide comprehensive coverage and avoid region-specific false negatives. Route priority optimization involves careful planning of priority ranges. Leave gaps between priorities 100, 200, 300, rather than consecutive numbers 100, 101, 102, to allow for future insertions without renumbering. Health check endpoint optimization means designing application health endpoints that are fast, comprehensive, and don't impact production performance. A good health endpoint checks critical dependencies but doesn't perform expensive operations. These optimizations can reduce failover times from minutes to seconds while maintaining system stability and avoiding false alarms that could cause unnecessary traffic shifts. Enterprise implementation patterns. Let's examine real-world patterns for implementing route taxonomy and health checking at enterprise scale. The command sequences shown represent production-tested approaches. The environment separation pattern creates distinct taxonomies for different operational environments. Notice how each environment gets its own policy space, preventing accidental cross-environment policy application. The Service Mesh Integration command shows how to integrate route taxonomy with service mesh architectures. The Service Mesh config parameter links routing policies to service mesh behavior, creating consistent policy application across network layers. The compliance integration demonstrates how taxonomy policies can automatically trigger compliance monitoring. Routes tagged with sensitive data policies automatically get enhanced logging, encryption, and audit trail requirements. The monitoring integration command sets up automated alerting when health check patterns indicate potential systemic issues. This proactive monitoring can detect problems before they impact users. These patterns represent years of enterprise experience and provide templates for scaling route management across large, complex infrastructures while maintaining governance and reliability.